Hello everyone. So I will start by thanking the organizers for giving me this nice opportunity to speak before you. I have just finished my PhD with my doctoral advisor Pinaki Chaudhary and going to join a postdoctoral position in University of Milan. So today I'm going to talk about designing a spatially inhomogeneous class where we can control the mechanical response. This work we have just finished now and still not published, and has been done with Pinaki at IMSC and Jürgen at the University of Düsseldorf. So there has been a couple of talks in last 3 days where people have already talked about various sorts of deformation of amorphous solids and their response. So one thing is very common about all these sorts of deformation is of inhomogeneous flow patterns. So as you can see here that when such material, for example this metallic glass, is deformed, so there emerges some inhomogeneous flow patterns, and you can see that some part of the material flows more than some other parts, and such inhomogeneous, so there is some band like a structure forms which is called shear bands, where relative mobilities of the particles are different, and such behavior has been observed in granular material recently, and also many other studies. And for example in this colloidal glass, where particles are color coded with their velocity, and you can see some particles are having relatively high velocity than the other particles, and such observations have been done in various computer simulations in different systems also. So now the question is, can we predict the nucleation of such shear bands in the amorphous materials? So as we can see here that in this particular study where the first one, where the shear transformation zones have been tried to predict by varying the protocols, but their claim is that is highly dependent on the protocol. If you slightly change the protocol, the nucleation of such shear bands completely changes. Similar in this particular study by Pinaki, Jürgen and others, so they have shown that in a binary Linares mixture at very small temperature, these shear bandings is completely stochastic. So they start with the same initial configuration of the material, and they change the thermal noise by changing the seed of the thermostat, and they see that these band patterns completely changes in different deformation, starting with the same configuration of the material. But very recently some study by Michael Falk and others, they have shown that it's possible to predict the shear band formation in a thermal aqueous thermal quasi-static simulation of material using some machine learning technique based on convolution neural network, but with some fair accuracy. But they already say in the paper that it's very difficult to predict the exact location of the shear band initiation into the material, and into the metallic glass is a stochastic process. So now it's very important to understand, is there any way to control, if we cannot predict with fair accuracy, to control the formation of such bands into the material. So this particular study where they try to create porous classes by introducing different sort of porosity or different sort of pores also, where you can see that they can able to control the yield strength, elastic modulus, and also the direction of propagation of the band. As you can see here is tilted one, and here it goes to completely the horizontal one as you increase the porosity. In this particular study, they have shown that if you introduce a void into a metallic glass, so you can control or initiate the shear band near the voids, and also you can see the early nucleation of shear bands. Very recently by Ozawa, Berthier and others, they have prepared very well annealed glasses, and they have introduced some soft zones which are basically equilibrated at slightly higher temperature, and they say that these shear bands nucleate from these soft zones. So in this way, in such a study, you can see that somehow they are able to control where the shear band is going to form. So my protocol of generating inhomogeneous glass is based on applying a temperature gradient. So I will tell you what happens to a glass very briefly if we apply a temperature gradient. So if we take some glassy liquid, for example in the supercooled state, and we apply a temperature gradient by having one end enclosed with some hotter region and other end enclosed with some colder region. So we see that some large scale mass movement and things happen, and ultimately you see a density profile which shows that density is small near the hotter end and higher near the colder end as expected. But the interesting thing happens in the context of glass, which I'll tell you. But in the supercooled liquid, if you remove this temperature gradient, this inhomogeneity in terms of density or other quantities that you have got recovers to again the homogeneous state. For example, the density will become flat. This thing we have studied in detail in this particular paper. But here we want to understand what happens to a glass which is below the glass transition temperature if we apply something similar type of temperature gradient. So again here the density inhomogeneity and other inhomogeneity you will see into the material, but you will not see the steady state because it take very large time to reach. And when we switch up the gradient, the homogeneous profile of the material is not recovered. The whatever inhomogeneity has generated into the sample, not exactly that, but some sort of inhomogeneity will be present into the material even if you remove this temperature gradient that you have applied to the material. So this is very similar to something like laser heating or laser welding, where you shine a laser to a metallic glass and you cause some local melting, which is like some large scale movement where laser is shined, and when you remove this laser, whatever large scale movement that has happened there is somehow trapped into the material, and you are able to get the deformation or the structural changes even after removing the laser that you have shined. So I would like to tell you the protocol that we have used to generate this inhomogeneous sample. So we have taken 80-20 Covendorson glass former, and for this glass former the mode coupling temperature is close to 0.435 and glass transition is close to 0.3. We prepare at first homogeneous glass at temperature 0.2, which is below the glass transition temperature, and then after we apply a temperature gradient by following this protocol where we do local thermostating at the temperature at which we prepare the glass, which is 0.2 near the colder end, and this hotter end is kept at slightly higher temperature than 0.2, and in this way gradient is in terms of temperature is generated from this region to this region and this region to this region, and some inhomogeneity is developed into the material. And as I already said, since this material is in the glassy state, we remove the temperature gradient and we see that some inhomogeneity which has been developed when the gradient was on still remains into the material, trapped into the material. So for example, you can see here we have a glass where the density is homogeneous, spatially not varying too much at the temperature 0.2. Before switching on the gradient, we switch on the gradient by having the same temperature in the middle and here slightly higher temperature, and you see that density decreases here and density is roughly same here, not too much variation, but because of decrease and roughly same here, so in between there is a hump kind of thing is there, and depending on like the time for which you keep the gradient on, your density profile keeps evolving with time. So you start from the blue one, you go to this one, and then you ultimately reach this one, and if you keep this gradient on, this profile will keep emerging. And ultimately when you switch off the gradient and you return back to temperature 0.2, so somehow this gradient profile in terms of density and other quantities that you have got when the gradient was on is remains there into the material. And these inhomogeneous structures, what we get, the first question is they are stable or not. So we see that these inhomogeneities which are there, they are present into the material after switching of the gradient for longer and longer time. So this is very important if we want to understand the shear response of these materials. So these structures are stable. Now what we do, we try to do, sorry, before going to that, just I would like to mention that there is inhomogeneity in terms of density, and since structural changes has also happened, so there is inhomogeneity in terms of potential energy into the material. So this inhomogeneity into the material depends on two factors. First is the temperature gradient, the strength that you apply by having one end at 0.2 and other ends at different temperature like 0.3, 0.4 and 0.5 and so on. So this keep changing, and also the exposure time, as I already mentioned, that the time for which you keep the gradient on, this also depends on that. So we can tune the inhomogeneity based on the time for which the gradient is on and also the size of the gradient. So we have been able to generate a spatially inhomogeneous glass at temperature 0.2. Now the goal is to understand the pathway of mechanical failure to these inhomogeneous materials. So we generate the inhomogeneity in the g direction into the material, and then we understand the shear response of this material by like shearing this plane. You have this one, and then you do this, and then you shear it like this. So the shear direction is this, and this particular plane is sheared. And we control the temperature at 0.2 at which the glass was prepared using the DPD thermostat. And this is the macroscopic response of the material for different temperature gradients that we apply and prepare different glasses. So you can see where temperature gradient is not applied is the dotted one, black one line. So we can already see that there is some change in the yielding behavior of the material. I'm not going into the detail, but there is some change. Some is like diminished and some is like becomes prominent here. And other thing is very clear from the potential energy we see into the material. So this takes very long time to reach the steady state, and you can see the strain values here. So this is because you have generated some inhomogeneity into the material, and since if you want to achieve the homogeneous flow behavior, this inhomogeneity has to go, which takes sufficiently long time to go actually. So now the microscopic response in the form of shear bands. So you can see the material which has not been exposed to the gradient. This has been exposed like temperatures 0.2, 0.4 and 0.2, 0.5, and you can see that there is a pattern in the shear bands that we can see. So for example, in this particular case, shear band nucleus into the middle, here shear band nucleus around the boundaries, and these are the different strain values at which you are seeing the snapshot. And now we actually measure the mobility of the material by measuring the square displacement of the particle to characterize the inhomogeneity, to characterize the mobility. And this now the question is there any control over the shear band formation? Just to characterize that, we plot this, scatter plot this here. So this is the mobility of the particle, and this is the like shifted local potential energy with respect to the total potential energy of the material. So these are the regions where particles are more energetic, and these are the regions where particles are less energetic. And this shifted potential energy thing is calculated at a strain value 0 where we have not deformed the material, and these are the mobility at a strain value of 0.1. So now we can see that for example, in different temperature gradients that we apply to generate the inhomogeneous glasses, that when the inhomogeneity is more, for example in this particular case, you are seeing that mobility is higher only for those particles which are highly energetic. And this particular trend reduces if we go closer and closer to the smaller temperature gradient when the inhomogeneity is decreased. And for example, when we don't apply any temperature gradient, purely homogeneous sample, here roughly the particles are equally likely on both the sides, highly energetic. So there are other factors which are governing the nucleation of shear bands here, but here inhomogeneity is controlling the shear band formation. So this is the movie where you can see this is the unprocessed sample where we have not applied any temperature gradient, and where we have applied the temperature gradient. You can see that shear bands persist for very long time, and also we have a control over the formation of shear band. Its nucleates, for example in this case, near the boundaries. So now the question again comes whether such shear bands are stochastic or deterministic. So in order to check that, we have again used the same sort of trick. We have 10 samples here starting with the same initial configuration, but we have changed the thermal noise to the thermostat, and we see that when we don't expose it to temperature gradient, the sample is completely homogeneous. These bands are roughly random, so you can see bands are emerging at different places. But in this case, in all the 10 samples starting with the same initial configuration, you can see roughly there is a pattern into the band depending on the temperature gradient that we apply. So for these cases, if your inhomogeneity is sufficient enough, so you are able to control the nucleation of the shear band, and you can see a pattern here in the shear band. So at the end, before I finish, I would like to mention another protocol that we have used to prepare inhomogeneous classes. This is based on method hybrid swap Monte Carlo and molecular dynamics. What we do here, so we take the material and we do molecular dynamics throughout the material, but in between we stop for some time after doing some number of MD steps to do swap Monte Carlo in a region of width W around the central region. So what happens? This swap Monte Carlo technique allows faster nucleus, faster annealing of this particular region, and we can see that in very long time we have profiles where, for example, this case no swap has been done, and this case where whole material has been swapped. So these are the limits, and here we have different widths of the central region where we do the swap, and we can see that this annealed better than these regions, and there is a barrier kind of thing is created. And here one thing is important, that these samples are roughly dominated by the variation in our heterogeneity in terms of the potential energy, not in terms of density. Roughly you can see density is varying a little bit, but not too much. So we have studied the similar type of shear response of these materials, and we see that here also there is a very clear control over the formation of shear band. For example, these are the poorly annealed classes. These cases you can see shear band is at random location. This is well annealed glass. Also shear band is random location, but shear band is sharper, which has already been reported by others. And in these cases shear band nucleates, for example, near the region where energy is higher near the boundaries. So in this particular case we have been also able to control the formation of the shear band. So now I will finish that we have been able to create inhomogeneous classes by applying temperature gradient, and also by doing this inhomogeneous annealing protocol, and we have been able to control the formation of shear bands by doing such protocols, and we hope to submit this paper soon. Thanks a lot for your kind attention.
So in any protocol, suppose you form the shear band, and suppose you keep on shearing for long time, does it always go to fluidized state, or
yeah, it goes to fluidized state. For example, here you can see this is the potential energy, and this is the case where no inhomogeneity is there, and this goes to the same state, but it takes very long time. You can see the strain is close to 20 when it reaches the steady state. So it homogenizes, but it takes long time.
I see. So this is unlike the case for if you have some attractive interaction or something where the shear band can persist for indefinite time, basically.
Yeah.
Okay. Thanks.
Okay, one more question maybe, if there is one. I had one. Are there cases where the shear band nucleates in the cold region as well? It looked like you had some of those.
Yeah. So for example, you can see the pattern here. So he's here. For example, in this particular temperature gradient, when we apply to generate the inhomogeneous classes, we see that shear band nucleates around the central region, and here in this case it originates around the boundaries. So this is a bit confusing initially, but we have been able to understand based on the energetic arguments. So for example, if you see the case of 0.3, so actually we don't understand completely why does it happen, but this is happening. So when we switch off the gradient, when the gradient is switched on, here the energy is higher, but for this particular case of 0.3 and sometimes also in the case of 0.4, what we see that this energy goes below the energy of the material, of the homogeneous material, even near the boundary. So this may be because of some local expansion and other type of things are happening, and the process is not so fast here, maybe that could be a region, but here the energy is lesser and energy is higher in the central region. So that's why we see that shear band nucleation for 0.5 case and maybe sometimes for 0.4 case also is happening near the boundary where energy is higher, but 0.3 case and a few cases of 0.4 we are seeing that this is happening near the central region where energy is higher.
Okay, great. Thank you very much.
Thanks.